Hello everyone, welcome back to Altium Academy. I'm your host, Zach Peterson. Today, we're going to be doing a deep dive of one of our 1-minute design review submissions from Yassine Jadid. And this design review submission was for a power meter PCB. Now, Yassine designed this PCB as part of a summer internship program, and I really wanted to look into it deeper in a long video because I think there are a lot of opportunities to make this design look much more professional. So let's hop into Altium and look at this design, and let's get started. Now in this video, we're going to take a look at a 1-minute design review submission in a bit more detail, and we want to find some opportunities to show how this design can be made much more professional. Now, I expect the design as it was submitted to be functional, and of course that is an important basic milestone for measuring success in any PCB project, but it's not the only measure of success. What we want to look at are some ways to make the PCB design package more professional, both in the schematics and in the PCB layout, and we're going to identify some changes that could be implemented in the PCB layout for purposes of EMI, EMC, and overall functionality. So with that, let's go ahead and jump into this project from Yassine Jadid. So here we are inside of the top level sheet for this design, and the top level sheet in this design actually contains the microcontroller that runs the whole system. Not a conventional choice, but perfectly acceptable from a project structure choice if that's what you want to do. Typically for the top level sheet, we would put like a block diagram if we were going to do a hierarchical design like this, and then we would put the MCU inside of one of those subsheets. But of course you can put it in the top level sheet if you want. One thing I would recommend that everybody do before you start diving in further into this video is to watch our Super Pro Schematics video, where we run over some of the features that we've seen in some of our design review submissions that we consider to be super professional, and you can see how to draw out all of those very professional looking features inside your schematic sheets in that video. So let's get back to this video. Now there's a couple things that we see already in this sheet just from looking at this. What we see here first is the file name. This is an SCH.dot file, and what that means is that this is a schematic template, not a schematic doc file. So we want to make sure that all of our schematics are actually schematic doc files and not schematic dot files. The other thing here is we see that we're getting an error because here in this JTAG block, you can see that the file name is also pointing to a schematic document file. But if you look at the file name in the project tree, you can see that the file name is a schematic dot or schematic template file. So again, we want to make sure that we use the same extension. We want to use a schematic document file for all of the sheets in the project. Otherwise, when we misname them, we're going to get these errors. And of course, schematic template files are meant to basically reuse details in the schematic templates in new schematics. So we don't want to use them as project level sheets. Now, just zooming out and looking at the microcontroller itself, there are a few things going on here that we need to address. So the first thing is the fact that this is a very large MCU. And I did mention that in the 1-minute design review video. And if you want to watch the original design review short, you can find a link in the description on this video. But if you take a look at the number of pins that are being used, most of the pins on this device are actually not being used. Now, this is an STM32. It does have a lot of pins on it, and I think people like to use these common microcontrollers because they probably learned how to use that microcontroller in classes in university, or they probably used it from tutorials because, of course, a lot of tutorials focus on the most common microcontrollers. So it is understandable that as a student or as an intern, you would focus on using one of these microcontrollers like an STM32 or an ESP32. However, if you want to make this project more professional, you should probably pick a smaller microcontroller that doesn't leave so many pins unused. One of the big reasons we might do that is, of course, to reduce cost in the design, because physically smaller microcontrollers just carry a smaller price. Another reason that we might want to do that is because that physically smaller microcontroller also occupies smaller board space, and of course that lets us make the board physically smaller as well. When the board is made physically smaller, then you can fit more boards into a panel, which means you can reduce the cost of fabricating the bare PCBs. All of those points regarding board size and cost are things that you would have to consider if you were designing this product to be produced at scale. Next, let's take a look at this other schematic sheet. Here we have a couple of things, which I can't tell you how many times I bring this up, and it's like nobody listens. But here you can see we have two ferrites. We have a ferrite bead blocking the 3.3 volt digital rail from the VDDA rail, and then we have another ferrite that is bridging two different ground nets, a GND-A or an analog ground, and then a main system ground. Now I can tell you with 100% confidence, you absolutely do not need FB2 in any way, shape, or form. Just delete it, use a single ground plane for everything in this design, aside from the DC-DC converter, which we will discuss momentarily. But specifically for everything on this microcontroller, just use a single ground plane covering all of the ground pins. Another reason to do that is because 99% of the time, these two pins are already connected inside of the microcontroller directly on the die. So there's no point at all in even separating them on the PCB. Next, let's go up to the rails up here. So here we have a 3.3 volt rail, which is powering our IOs, and it's isolated from an analog power rail using a ferrite bead. And I see here that we have the classic 100 megahertz ferrite bead in a chip form factor. And I'm actually surprised because this one is a 1000 ohm ferrite bead, and typically we see a 120 ohm ferrite bead. So I guess you get some points for uniqueness there. Bottom line is, for this ferrite bead blocking the digital rail and the analog rail, you probably don't need it at all. What you can do if you really want to try using it is you can build the board and populate FB3, and then again, you can test this on an oscilloscope, and you can compare the case with a 0 ohm resistor bridging these two rails. Then you can really see whether or not there's a difference in the noise reaching the analog rail. Now, if you want to see what the experts have to say about these usages of ferrites, you can check out one of the videos linked in the description. Now, as I click through some of these other schematic sheets, you can see here that we do find some components that also have multiple ground nets connected. Now, I do expect that because here in the power supply sheet, you can see that we have an isolated DC-DC converter, and there is a 4 kilovolts isolation voltage specification on this transformer. Now, we'll dive more into this DC-DC converter momentarily, but you can see here that we do have two separately named ground nets, which are separated by a capacitor, which is the correct practice. However, on this energy meter chip, you can see here that we also have separated ground nets, which are explicitly named on this chip. And then you can see here, we also have ferrites that are being used to bridge across these ground nets. Now here I've pulled up the application schematic, and you can see here inside of the application schematic that they don't even recommend using ferrite beads. And you can see here that they do have differently indicated ground nets, but you can see here that they do connect them back together, as you can see right here in this lower left corner of this schematic. Now, furthermore, if you search for galvanic inside of this datasheet, nothing comes up. So there is no galvanic isolation specification on this component. So there's no reason to have separated ground nets. And of course, connecting the ground nets back together with a ferrite bead will eliminate the galvanic isolation at DC. So again, you have to make sure that you follow those grounding recommendations, not just for the functionality of this chip, but of course for EMI and EMC purposes as well. Now, as I click through these other schematic sheets, I do see the ground nets that I would expect to see for these different circuits, but I saw something that looked a little weird, which was in this 16 megahertz clock sheet. Now, in this clock sheet, you're using a port for the ground connection. You really don't need to do that. You can just use a ground symbol because ground symbols and power symbols are global inside of Altium. Now, the last points I would like to bring up here around grounding is in relation to the use of this capacitor across the primary ground and the secondary ground. Now, it is good practice to bridge the primary and secondary ground in a DC-DC converter using a class Y capacitor or a Y-type capacitor. And these are capacitors which will have a specific failure mode if they do exceed their rated voltage for whatever reason. Now, here you can see we have a 6 kilovolt rating, and this is on a 4 kilovolt isolation requirement. So the specification is fine. Typically, if the capacitor is placed for connecting these two grounds, as you can see here in a DC-DC converter, the capacitance is a bit larger, such as 1 nanofarad. This is only 470 picofarads, so consider swapping it out. But here you have to actually make sure that this is a class Y capacitor. Now, I looked up the data sheet for this capacitor on Octapart, and it is a Y dielectric, so it's a Y5U dielectric, but that does not mean that it is a class Y or a Y-type capacitor. The difference between class X capacitors and class Y capacitors is what happens when they fail. Class X capacitors will fail to short, while class Y capacitors will fail to open. This means if there is a fault in the system and the voltage across this capacitor exceeds its rating of 6 kilovolts, it will fail to an open circuit. That way you won't have a short between those two grounds, which could potentially allow that very high voltage to flow across those two grounds and then create a safety problem or destroy other components in the system. Now, that isn't explicitly stated in this data sheet for this capacitor. Whenever you're going to use any capacitor in a safety application, just make sure you know whether it is class X or class Y and what its failure mode is. The last thing I want to bring up on this DC-DC converter is the transformer itself. Now here, if we zoom in on this transformer, we can see that this is a multi-tapped transformer or a multi-winding transformer. You can see here in the description that we just list transformer core. However, if we look at the footprint inside of the PCB layout, you will see that this is actually a coil former, not a core. So here you can see the part number right here for this transformer, and it matches the part number right here in the schematics. Now, if you Google this part number, you will see that this is indeed a TDK coil former, not a transformer core. So again, make sure that you specify what this component is before you export your bill of materials. But it would be a good idea to do one of two things. Either here in the description, you should put the part number for the core, and TDK does manufacture core materials that are designed to fit these coil formers. So you can put the part number that you want to use for that core right here in the component description, or you can create a dummy component somewhere else on this sheet that doesn't actually mount anywhere on the PCB, and then that dummy component will then get included inside of the bill of materials. The other thing you should do in this design is you should create a transformer assembly instructions document, and that's basically why someone would use one of these core and coil former pairs in a design like this. It's because it is going to be hand assembled. Now, I've done a video about this in the past. You can check out that video link in the description to learn more about using core and coil former designs for transformers. But what I'm going to say here is that you should create this assembly document because, of course, this is a Weebench design, and in those Weebench designs, they require you to do this custom assembly for this transformer in order for this design to work. Now, typically, the newer Weebench designs will actually spit out an assembly document for that transformer, especially if it uses like these core and coil former pairs. Here, this transformer assembly document should look something like this. You basically have the core part numbers and the coil former part number specified in the document. Here you have the core and winding details for all of the different taps on this transformer. And then here you have some winding instructions that lists the number of pairs, what is the wire gauge, how many turns, what's the winding direction, anything that anybody would need to hand assemble this transformer. Now, after it's assembled, it's going to have to be tested, and it can be tested with a simple LCR meter, and we've done that in another video as well. And you can see here we have a primary inductance target that we're trying to hit. We also have a number of primary and secondary windings, and you can test what is the output inductance of that primary coil just using an LCR meter after this is assembled. Now, there is one thing that I often bring up in design reviews, which is parameterization of the parts that appear in your schematics. So what is parameterization? Well, it refers to all of these parameters that you see here in the properties panel, which describe the various properties of this component. And there are two really important parameters that you should always include in your parts. One of these is the manufacturer name. As you can see here for this diode, it is Diodes Incorporated. And then you should also include a manufacturer part number. And as you can see, we have a manufacturer part number right here. Now, as I click through to some of the other sheets in this design and I select some of the parts, you can see here that the parameterization is not consistent. So what that means is that you have different names for different parameters, or some of the parameters are missing. So for example, on this Schmidt trigger component, you can see here that we have a manufacturer name, but we don't have the manufacturer part number as a parameter. Instead, it's listed here as a comment. If we look back here in the power supply sheet, for example, you can see here that if I select B1, you can see that we have inconsistent naming. So we have manufacturer part num, but not the full name, manufacturer part number. And then here we have the parameter manufacturer name instead of just manufacturer. It doesn't really matter what the name of the parameter is. What really matters is that they're just consistent across all of your parts. So pick a name for the parameter and use it everywhere, even in your libraries. Now, I know what some of you out there are thinking. You're probably going to say something like this.
I'm just going to have my manufacturer source my part. I don't really need to worry about the part number.
Or you're probably thinking something like this.
Writing out all those parameters takes too much time. I'm just going to do it by hand in an Excel sheet.
Let me show you why this is so important. If we go here to an out job file and we create an export for a bill of materials for the entire project, we can actually configure which columns get selected for automatically exporting that bill of materials into an Excel format. So to do that, we would go to configure this bill of materials export. We'd select the columns option in the properties area, and we would scroll down to look for all of our different part number options. Now here you can see we have all of these different column names that appear across all of our parts in the design. Now here, if I turn on, for example, manufacturer part number and manufacturer part num, you can see here that only some of those manufacturer part numbers actually exist in the design. We don't even know what those other part numbers are unless we look over here at the comments section. And for a lot of these part numbers, there hasn't been a part number chosen at all. Next, you can see here, if I scroll down a little bit, we have another set of parameters, which are part number, and then part number, but without a space between part and number. So you can see here, we already have 4 different columns that we're gonna have to consolidate when we export our bill of materials into an Excel format. This means you're gonna have to copy and paste, or you're gonna have to enter in a formula that then puts all of those part numbers into a single column. Why do we need to have all those part numbers in a single column, you'll ask? Well, wait until you go and try and order stuff from DigiKey or Mouser and upload a bill of materials with 4 different manufacturer part number columns. It's a big pain. Also, if you send this kind of bill of materials to your manufacturer where you have blank entries and you have entries in different columns, your manufacturer is going to send this thing back to you and tell you to fix it. If you just use consistent parameterization throughout the entire project and in your libraries, you're not going to have this problem. All of those part numbers are going to appear in the single column, and then when you export to an Excel file, you'll have those same part numbers in a single column. It's extremely easy to keep it all organized and extremely pleasant to look at. Next, let's take a look at the PCB layout. You can see here in the PCB layout that everything is present in the design. We have everything routed. We have what looks like a nice outline here, outlining the area where we have our galvanic isolation, and we have some mounting holes. We basically have all of the features that we would expect to see in this kind of design. Now, one thing I will say, for a power meter, you do see here that your LCD screen sits much lower than some of the components on the top layer. I would consider putting that LCD on the back side just for functionality and user experience purposes. If we look on the back side, we do have components back here, but they are pretty flat and low profile. So the tallest component on the back side would be your LCD screen. The other thing you might consider doing in order to keep this board a little more low profile is to take this very large capacitor and have it bent over at a right angle so that it sits across the surface of the board. And finally, screw connectors, just like these terminals, can be very convenient, but of course they are also a bit tall. There are some alternatives out there that could give you the same voltage and current rating, but that are a little bit shorter and they won't sit as tall above this relay. So those are some things that I would do in this type of design, but let's get a little bit deeper into some of the functional issues in this PCB layout. Now, first things first, I did not run a design rule check as part of the 1-minute design review. I wanted to save it for this video. So I'm gonna run it right now, and let's see what exactly happens with this design rule check. You can see here that we only have 6 violations. Really good job here, because sometimes we see design review submissions that have 600 violations instead of 6 violations. And I can already guess what a few of these violations are. Here we have silk to silk clearance because we did have what looked like overlapping silk screen in the PCB layout, and then we have silk to solder mask clearance, which are actually pretty simple to change. And in fact, you do have a really big clearance value listed here for the silk to solder mask clearance. These aren't the default values, but they are pretty large. And if you go with a more realistic value that you could find on the manufacturer's website, you're going to be able to resolve those design rule errors very quickly. Next, there's a few things that I want to look at in the overall structure of this PCB layout. So first things first, you can see right here we have the footprint for that ceramic capacitor that's being used as a safety capacitor. What you should do is actually move that closer to the transformer so that it basically provides a return path across these 2 ground nets that goes along the transformer. You also want to make sure that the capacitance for this capacitor is larger than the winding to winding capacitance on your transformer. That's going to ensure that you can actually control the return paths across these 2 ground planes. Next, as I'm looking around here, I do see that you have a lot of thermals everywhere, and that means that you didn't update the default thermal attach rule. Now, thermal attach is definitely needed on these through-hole components such as you have over here in this part of the layout, but they aren't always needed on these surface mount components that you can see here on this IC, or that you can see up here on your STM32. For something like this, where you just have a small polygon connecting to these surface mount components, I always recommend just removing the thermal attach. You can do that by updating the default design rule in the PCB Rules and Constraints editor so that you have direct connect instead of a thermal connect or relief connect. The next thing I'm seeing is on your vias. You have thermal attach on your vias. Thermal attach on vias is totally unnecessary. You can go ahead and remove that entirely. Just set all of your vias to direct connect. Now, the savvy viewer will notice something in this via that I just selected, and if I zoom in right here, you'll know what it is. Here you see that this is a 1 to 2 layer span via, but if you look here along the bottom of the PCB editor, you'll count up 4 layers. That means we are using blind vias in this PCB layout. Now, blind vias are fine to use if you actually need them and if you get the StatBook qualified with a fabricator before you create the design. But here, when we go into the PCB StackUp and we go to the via types tab, we see that we have via types that we're not going to be able to manufacture. Here you can see we have a blind via going from layer 1 to layer 3, and then another blind via going from layer 2 to layer 4. These overlapping blind vias are unable to be fabricated at all. You cannot have mechanically drilled blind vias that are crossing each other like you have here. This is due to a limitation in the stack and drill and plate process. So you're not going to be able to fabricate these 2 vias. Furthermore, you have plenty of room in this design. This is not a high density design. There are no BGAs in this design, so you don't need to have blind or buried vias at all in this PCB layout. I would just stick to through holes because you have plenty of room in this PCB layout to accommodate that room that you need for through hole via routing. And of course, bringing this back to some of the things I mentioned earlier about cost. If you eliminate those blind and buried vias from that stack up, you will significantly reduce the cost needed to fabricate a bare PCB for this design. And speaking of our vias, I want to look at some of the vias that are attached to these lines on your integrated circuits. Here you can see that we have a via that looks like it has a pretty small drill diameter. And if I select this, you can see what that drill diameter is. Here we have a 20 mil diameter pad, which is a good size pad, but we have a 7 mil diameter via. So that means your fabricator is going to drill this with a 7 mil diameter drill. Again, this is not a high density design. We're not doing BGA fan out here or anything like that. You really don't need to have a 7 mil drill for these vias. You'll reduce cost and you'll still be able to route everything in this board if you use a larger via drill diameter. I would suggest using 12 mils or 14 mils because that is going to be much cheaper to fabricate, and like I said, it's not going to take up any extra room in this design. Once you select that via hole diameter, make sure you apply the appropriate pad oversize. So in the case of a 12 mil diameter, you could keep the same pad oversize that you have here, and you would just set your pad size to 25 mils. Once you have the appropriate via type set, you should then apply stitching vias to the GNDP net and the GND net so that you can stitch them together throughout the entire stack up. You have polygons on multiple layers which need to be connected together, and you don't have very many vias that are being used to do that. So I would recommend using the stitching via tool to stitch all of those rails together so that they're all connected in multiple places throughout the stack up. And the last point about vias, you can see here that we have a die-attached ground pad on two of your integrated circuits. Here you have the energy meter circuit, and then you have the STM32. So you want to make sure that you apply some thermal vias in that die-attached pad, which are then connected to the ground net. That is going to help dissipate heat and move it away from those chips during operation and help spread it around the board, create a more even temperature distribution. And the last point I want to bring up in this video is in relation to the outline of this board. Now you can see here that we can kind of see the board outline, but here on the right side, we see that the polygon runs right up next to this board outline. What you should do is you should go into the PCB rules and constraints editor. You should go to the board clearance outline section and create a new rule for the board outline clearance. Typically, we want to set a 10 mil clearance everywhere, and we can then go ahead and hit OK. And then if we re-pour our polygons, you'll then see that it automatically applies that 10 mil clearance everywhere. If you don't have that clearance when you go to manufacture this board, the manufacturer is going to send it back to you, or they're going to ask if it's okay to resize your board to allow for some clearance to that copper. This needs to be done because when the board is depanelized, if the copper runs right up next to that board edge, it could appear through the edge of the fabricated PCB. So we need to leave some of that clearance there to ensure that when the board is depanelized, there's no copper peeking through the edge of the PCB and creating a risk of a short. Now there's something very important electrically that I have to point out in this design, which is the clearances here to your 240 volt DC net. Now here you can see that we have a 240 volt DC net, and this polygon should be pouring over this pin, and I'm not sure why it's not, so you need to check your polygon pour settings. But here you can see that we have very tight clearances between this polygon at 240 volts and then these other nets in the design. So if we just do a quick measurement, you can see here, if I just do this measurement, we have 15 mils or 0.381 millimeters on the surface layer. Now, of course, these are all covered in solder mask, and that will impact the required clearance, but is 15 mils enough? Well, we can figure that out by using an IPC 2221 calculator. And you can see here that we have the IPC 2221 calculator article pulled up on Altium.com. Now, if I scroll down here, you see that there are two standards you can use. One is IPC 2221B, and the other is IPC 2221C, and they have slightly different definitions. But we're going to use the IPC 2221C calculator, as you can see here. Now here what we want to do is calculate the clearance that's required for external conductors that are covered with solder masks. So we want to look at column B4 in the standard. And the value for the clearance requirement in column B4 can be found from this table. So you can see here that the required clearance is 0.8 millimeters. 0.8 millimeters is basically 32 mils, and you have a clearance of 15 mils. So you're going to need to increase those clearances to at least 32 mils. I would recommend just setting it to 1 millimeter or 40 mils just so you have some margin. Now, of course, there's more I could go into in this video, but as you've watched this video, you've probably heard me mention several other videos that I've made on some of the topics we've discussed in this deep dive. So make sure to check out the video links in the description if you want to learn more about some of the points that I mentioned in this video. Thanks for watching this video, everybody. We're going to be doing more of these deep dives of the 1-minute design review submissions. So if you enjoy the 1-minute design review shorts and you enjoy these deep dives, make sure to hit the subscribe button and hit the like button. And of course, leave your comments and questions in the comment section. And if you ask a great question in the comments section, it just might end up in one of these videos. Thanks again for watching, everybody, and don't forget to call your fabricator, folks. We'll see you next time.